So now we are going to do the next thing, resonance absorption of energy. So how does the spring system absorb energy? Okay, and the NMR experiment. So the NMR experiment depends upon resonance absorption of energy or absorption of energy by the spring system from the external source. Okay. So let's look at it in a classical picture to begin with. Let us consider the following situation. I have the magnetic moment spinning, precessing in this way. This is mu, x-axis, this is minus y, this is the y-axis, and this is the z-axis. And this precessional frequency is, let's call this as omega naught. Precessional frequency is omega naught, and that is minus gamma. Okay. Now I apply another rotating field in the transverse plane. So this is my transverse plane. I apply another small field. Okay. This field rotates here. This is a rotating field. This has an amplitude h1 and has a frequency omega. So this rotating field I call, I represent it as, this is the rotating field which you apply, and let us call this as h1 e to the minus I omega t.
What is the meaning of rotating field?
So it goes with the frequency. There is a field which is rotating in the xy plane. It's not fixed. Okay. So it's a small field. Small field. It is as if you are having a small bar magnet. Well, bar magnet is a loose analogy, but you have a small magnetic moment which actually goes around. Here it is a static field, right? You have a static field. Here is also a field with an amplitude h1, but it is not static. It rotates in the xy plane, and therefore we call it as a rotating field. And this is h1 e to the minus I omega t. Why you call this as a rotating? Why do you represent a rotating field in this manner? Exponential. So does everyone know that rotation can be described by the exponential time dependence in this manner? Because you can always expand this as cosine omega t minus I sin omega t. The two components are changing, and therefore it is a rotating field. Now what you do? You sit on this rotating field. Okay? Sit on the rotating field and look at the nucleus. In other words, you are going into the frame of reference which is rotating. So that is called as the rotating frame transformation. You go into the rotating frame. You sit over the RF and look at the nucleus. So in the rotating frame, what is the precessional frequency? Precessional frequency is omega naught minus omega. Okay. When you sit over it and look at the field, obviously it is going at a different frequency. If the direction of motion is the same as the direction of motion of the spin, then it is a difference, otherwise it is a sum. Okay? So in this case we are considering the motion in the same direction as the spin. Okay? And then this difference, if the precessional frequency is omega naught minus omega. Now, you have the control over omega. This is generated externally. Okay, by your equipment, by your instrument, this frequency is generated. Of course, you also have a static field which is generated externally, but that you don't change it. It is a constant field. H0 field is a constant field, and that happens in megahertz range. Okay, frequency, that energy corresponds to megahertz frequency. This also is in megahertz range, but you can control this. This is generated by your electronics, so you can control what frequency you want to generate. Therefore, you can vary this frequency. Omega you can vary. So, which means if omega becomes equal to omega naught, then you have reached a resonance condition. Omega is equal to omega naught means a resonance condition. Yeah? So what happens then? When it is in the resonance, it doesn't precess at all. It is static. So your nuclear spin is static. In that frame of reference, it is static. Now what does it see then? It doesn't see the H0 field, or the H0 field is then 0. If it doesn't precess at all the Z direction, that means there is no field there. So in the rotating frame, there is no field along the Z direction under resonance condition. But there is another field, and that is this H1 field. H1 field is in the transverse plane, because you are sitting over it, it is in the transverse plane. Okay? Then this spin will interact with your H1 field.
No, how there will be H1 field, because we are sitting on the same application.
Yeah, but this H1. This H1 this is the amplitude of the field. This is the amplitude of the field, and this is the frequency.
No, here where we are sitting on the H1, on the field are
No, on the field. But the amplitude is there. You're an observer there. You're an observer sitting on the H1 field. You're not blocking H1. Okay, so the field is present. So you are only observing sitting over there. Okay. In other words, you are trying to say you are going into the rotating frame of reference to see what is happening to your nuclear spin system. So there will be interaction between mu and your H1. Okay, so what should happen? It cannot remain on the Z axis anymore along that original direction which was, it cannot remain over there. So it has to tilt. It has to tilt. The net magnetization tilts. Okay, so that is absorption of energy. When there is a deviation, yeah, you have.
Sir, before reaching the resonance condition,
Yeah.
why this flipping is not happening? What is doing that H0? And if it is not precessing with omega naught frequency, why this tilting is not happening? Because H1 is also present there.
Yes, H1 is also present, but the efficiency of the transfer will be much less. It can happen then also. To the extent that it can cause a transition, it will happen. But the amount of energy absorbed will be small. It will be maximum when the resonance condition is satisfied. Okay. Interaction does happen. But when there is, I will show you that when you actually want to go into the Fourier transform, there will be interaction, there will be tilt. Even when it is off resonance, there will be a tilt. But that will create a new field which is called B effective or the H effective. So there will be orientation with respect to the H effective. Then also it causes a tilt. So the moment you apply an RF, when you apply an RF, it causes a transition. Certainly it causes a transition, but the efficiency of the transition and the absorption of energy by the spin system will be maximum when you have the resonance condition satisfied. We will calculate the line shape and we will show how the energy absorbed is maximum when this condition is satisfied. Okay, we will do all of that.
Sir, please again explain why is it maximum at the resonance condition?
If you come, because the interaction is maximum. See, when the two things are stationary, they see each other much better. See, if you are going into parallel trains, for example, you are in one train, your friend is on another train. And when two things are going parallelly, when they are exactly at the same speed, you can keep on talking for hours. Right? But if one is faster than the other, slightly faster, then you can only talk for some time. Interaction is limited, no? It's the same thing.
Even we can jump to the next.
You can jump to the next train. So this is a very similar analogy. Okay. Yeah, and in terms of the energy levels, we can also explain that. You have the two energy levels here. The energy separation between them is delta E. And this we already said is equal to mu h naught by I, and for I is equal to half, this 2 mu at h naught, and this is equal to minus gamma h naught h cross, or this is also equal to omega h cross. Okay, so therefore the resonance condition also implies that if you supply energy corresponding to this, there will be absorption of energy. When you have an RF whose frequency is matching this energy difference, then there will be absorption of energy and there will be transitions from the ground state to the upper state. So at resonance, RF induces transitions between the two levels. This is the quantum mechanical equivalent of the classical description which we had. Now, when we apply an RF is an electromagnetic radiation, right? When you apply this radio frequency, it is an electromagnetic radiation. Electromagnetic radiation you describe not as a rotating field, but as an oscillating field, right? So this RF is 2 times H1 cosine omega t. I can write it as cosine omega t or sine omega t, it doesn't matter. It is it's an oscillating field. Okay. Now how are the two things equivalent? So you can build. Yeah, sorry.
2 times H1.
Yeah. That is, you can put 2 arbitrarily. The reason I will see very quickly. Okay, why I put this? This is equal to e to the I omega 1 t plus e to the minus I omega 1 t. So you see that already? The factor 2 below has gone there.
H1.
Sorry, H1. So when I apply an oscillating field like this, in fact I am actually generating 2 rotating fields, right? So one which goes in the same direction as your spins, and the other one which goes in the opposite direction. So which one of these causes a transition? In principle, we can say both can cause transition. But now here the classical description which we had becomes useful. We saw if it is in the same direction, there is an better interaction, and therefore there is a better. And the other fellow will not see this spin at all. It goes. The two things are going in opposite direction. They don't see them at all, and therefore there is no interaction. However, it has some other implication which we will not do now. That is, it causes what is called as the Bloch-Steinert shifts later, and we can see that later. But that also plays a certain role when the power is very high. Other than that, this is only one component of this. Even though you apply an oscillating field, is one component of this which actually causes a transition from the ground state to the higher state.